Hi, everyone. Let's talk a little bit about 9.1 significance tests. So we already learned about the first topic in statistical inference, which is confidence intervals. Now we will learn about the second topic, significance tests. And you'll hear me refer to these as hypothesis tests quite often. Those are interchangeable terms. So, a significance test or hypothesis test is a formal procedure for using observed data to decide between two competing claims called hypotheses. The claims are usually written as statements about parameters. So, when we say parameters, we mean P, the true population proportion, or mu, the true population mean. There could be others, but in an AP class, that's what we need to be concerned about. All right, the claim that we weigh evidence against in a significance test is called the null hypothesis, or we abbreviate it as H naught, like this. You say this little sub-zero as naught. The claim that we are trying to find evidence for is the alternative hypothesis, or HA. I would say H alternative. So, for example, a free throw shooter claims that his long run proportion of made free throws is P equals 0.8, but we suspect that the player is exaggerating. So we'd write the hypothesis like this. The null hypothesis, or H naught, would be P equals 0.8. That's the player's claim, versus our hunch that it's less. The alternative would be P is less than 0.8. The alternative hypothesis is a one-sided test or a two-sided test, and it looks like this. A one-sided test, the alternative is either less than or greater than. A two-sided test is, we have the alternative is not equal to. And notice in all of these, the null hypothesis or null hypotheses are all equal to. We always make the null hypothesis equal to a specific claim. So read this example, and then we will talk about the solution. All right, so we write the null hypothesis as P equals 0.697. That's the Bureau of Labor Statistics claim, versus Jacob's hunch, P is greater than 0.67. And we're going to define the parameter as this. P equals the true proportion of all last year's graduates at Jacob's school who enroll in the college or university. And we need to take some caution. The hypotheses should express the belief or suspicion we have before we see the data. It's inappropriate to collect data and then form a hypothesis. I think unethical is too strong of a term, but let's say inappropriate to do that. And a little tip for the AP exam, hypotheses always refer to a population, not a sample. Be sure to state H naught and H alternative in terms of the population parameters. It is never, ever, ever correct to write a hypothesis about a sample statistic, such as using p hat or x bar. When you state a hypothesis, never use p hat, never use x bar, always p or mu. We have this idea of p-value, and it's a big, huge concept. We've already been front-loading the idea of a p-value. Let's get a little bit more formal with it. The p-value of a test is the probability of getting evidence for the alternative hypothesis H alternative as strong or stronger than the observed evidence when the null hypothesis H naught is true. All right, let's read this example, and then we will talk about the solution. All right, let's explain what it would mean for the null hypothesis to be true in this setting and interpret the p-value. For part A, if H naught is true, then the proportion of all last year's graduates at Jacob's school who enrolled in a college or university is 0.9. That number is 0.697. And for part B, assuming that the proportion of all last year's graduates at Jacob's school who enrolled in a college or university is 0.697, there is a 0.018 probability of getting a sample proportion of 0.85 or greater just by chance in a random sample of 40 graduates. More in making a conclusion, we make a decision based on the strength of the evidence in favor of the alternative hypothesis and against the null hypothesis as measured by the p-value. So basically, if the p-value is small, we reject H naught and conclude that there is convincing evidence for the alternative hypothesis, and we would write that in context. If the p-value is not small, we fail to reject. Let me say that again. We fail to reject H naught and conclude that there is not convincing evidence for the alternative hypothesis, and we would write that in context. So how small does a p-value have to be for us to reject H naught? Well, in chapter 4, we suggested that we use the boundary of 5% when determining whether a result is statistically significant. That's equivalent to saying that we view a p-value of less than 0.05 as small. And sometimes it may be preferable to use a different boundary value like 0.01, 0.10 when drawing a conclusion in a significance test, but the standard is usually 0.05 or 5%. The significance level alpha, this is the Greek letter alpha, kind of looks like a little fish, is the value that we use as a boundary for deciding whether an observed result is unlikely to happen by chance alone when the null hypothesis is true. Sometimes we'll call this the alpha level. And so the p-value is less than alpha. If the p-value is less than alpha, we say that the result is statistically significant at the alpha equals blank level. And again, alpha should be stated before the data are produced when we are composing our hypothesis. It's inappropriate to state your alpha after you collected data. All right, read this example and then we'll talk about the solution. So what conclusion would you make about at the alpha equals 0.05 level? Because the p-value of 0.023 is less than alpha equals 0.05, we reject H naught. We have convincing evidence that the true proportion of all cars in this highway are speeding is greater than 0.2 or 20%. So again, I want to restate that we never, ever, ever accept H naught. We never conclude H naught is true. We only have evidence to reject it. And an exam tip, we recommend that you use the following two-sentence structure from the example when writing the conclusion to a significance test. The first sentence should give a decision about the null hypothesis. We either reject H naught or fail to reject H naught based on an explicit comparison of the p-value to a stated significance level. The second sentence should provide a statement about whether or not there is convincing evidence for H alternative in the context of the problem. So if you go back to this previous example, we can see that we have that first sentence, we reject or fail to reject. In this case, we rejected H naught. And then we talk about the evidence that we have for the alternative hypothesis. All right, type 1 and type 2 errors. This is a big topic, but luckily the AP curriculum has really whittled this down in recent years. So when we draw a conclusion from a significance test, we hope our conclusion will be correct, but sometimes it will be wrong. And so when it's wrong, we either have made a type 1 or a type 2 error. A type 1 error occurs if a test rejects H naught when H naught is true. That is, the test finds convincing evidence that H alternative is true when really it isn't. And a type 2 error occurs if a test fails to reject H naught when H alternative is true. That is, the test does not find convincing evidence that H alternative is true when really it is. And so this little chart down here kind of shows us where we want to be is, well, let me talk about this. This is the truth. This is reality right here. And this is our conclusion that we've made based on our hypothesis test, significance test. And so if we reject H naught when H alternative is true, we've made the correct conclusion. That's where we want to be. Or if we fail to reject H naught when in reality H naught is true, we've made the correct conclusion. Now, a type 1 error occurs if we rejected H naught when in reality H naught is true. Or we've made a type 2 error when we fail to reject H naught when in reality H alternative is true. So these are bad. These can occur, but if you practice quality statistics, um, they are unlikely to happen, and you're likely to make the correct conclusion the majority of the time. All right, so let's read this example and then we'll move on. All right, so let's describe a type 1 error and a type 2 error in the setting and in this setting and give a possible consequence of each. So type 1 error is the police department finds convincing evidence that more than 20% of cars on this highway are speeding when the true proportion is really 0.2. The consequence of this would be the police department installs the speed sensors and traffic cameras on the highway when it isn't needed, which wastes money. And a type 2 error would be the police department does not find convincing evidence that more than 20% of cars on this highway are speeding when the true proportion is greater than 0.2. The consequence of this would be that the police department does not install the speed sensor and the traffic camera on the highway when it should. People would continue to speed on the highway, putting their safety and that of others at risk. So probability of a type 1 error is equal to the alpha level. So it's really easy to calculate. The probability of a type 2 error is more complicated, and we'll learn a little bit about that in 9.2. But what you need to know for this section is that the probability of a type 1 error is equal to alpha. And comparing the type 1 and type 2 errors, we can decrease the probability of making a type 1 error in a significance test by using a smaller significance level. But there's a trade-off between the probability of a type 1 error and the probability of a type 2 error. As one increases, the other decreases. If we make it more difficult to reject H0 by decreasing alpha, we increase the probability that we will not find convincing evidence for H alternative when it is true. So that's like I mentioned, that's a big topic, and we will learn a little bit more about it as we continue in this chapter. All right, so that's it for 9.1. I hope this was helpful. Thanks for watching.